you so much, and thank you so much for inviting me. It's a pleasure to be here. So, as Jing was just saying, my background is from this classical general relativity background, and I somehow started to become more and more interested in astrophysics when I was a PhD student. And I learned that neutron stars are the most interesting way to apply general relativity because you can actually study the neutron star itself. And with black holes, nowadays you can talk about studying the black holes, but for a long time, really what you were studying was accretion disks around black holes, which, you know, is interesting, but I wasn't as excited about this. Now, what I have here is an animation of a general relativistic toy model of a neutron star with a hot spot, and you see it's gravitationally lensed, and it's a fairly realistic representation of that, and it's being observed by the nicer X-ray telescope here on the International Space Station. And so I'll tell you a little bit about that as we go along here. So I think this is a crowd that probably knows a fair bit about neutron stars and stuff. I'll just give you my quickie overview. First of all, we take a neutron star. We don't know exactly how big they are, but the approximate size means that it fits pretty nicely in Toronto with U of T right here in the center. They're really very interesting just because they have really high density and very small radius. And so your typical size of a neutron star is around the same as the mass of the sun, but its radius is about 10 to the power 5 smaller, and which means that you have very strong gravitational fields. And this means that general relativity is super important for understanding the structure of a neutron star. It means that the escape velocity is a good fraction of the speed of light. It also means that a neutron star could conceivably spin with a velocity that is getting close to the speed of light. By close, I mean like 10 or 20%, which is pretty significant. And in fact, we would say that the maximum rotation rate that you could have is approximately 1,000 hertz. And this is a very approximate, which is kind of cool. It means that you're really able to probe relativistic effects with neutron stars. And just as for some Canadian content, since that's important here, I know, I'll just comment that the fastest known neutron star, 714 hertz, discovered by Jason Hessels, who is an undergraduate student at the University of Alberta and studied. I turned him over into the dark side. I'm very proud of that. Anyways, although he found that with Vicky Caspi at McGill. Okay. So, you know, at first state, you could say, well, a neutron star, it's just neutrons, right? Which is totally wrong. But you could say your first approximation to a neutron star is to say, well, you got a Fermi degenerate gas, and so you got your purple neutrons, and you're trying to squeeze them close to each other by making a very dense system, but the Heisenberg uncertainty principle is not going to allow you to squeeze them. It's going to give you a degeneracy pressure. And so that just basically gives you a momentum, which gives you an effective pressure. And the important thing is that as long as you are in a regime where your temperature is relatively low compared to the Fermi energy, you can call your system effectively zero temperature. And that is because the Fermi energy of a neutron star is very, very high. We expect at the kind of densities that we might expect at nuclear density that you're talking about an MeV, for most astrophysical processes, if we sort of ignore LIGO for a second here, or the birth of a neutron star in a supernova, most processes where you have a neutron star that's more than a couple years old are going to be basically cold. And so the most important thing about a neutron star is we call it a neutron star because you have a very dense system, and it can become very favorable when you get very degenerate electrons for the electrons to actually combine with the protons and give you neutrons instead of the normal beta decay that you would normally expect. But there's a lot more to neutron stars than that. So we just call them neutron stars just because they tend to be neutron rich, but there's probably a lot of other important things in there. And in particular, we don't know exactly how dense it can be, but we think it's the upper limit to how dense you could have the center of a neutron star is on the order of more than about 10 times the density of nuclear matter, which we don't really know that much about from experiments here on Earth. So there's a lot of uncertainty about how really dense cold matter behaves. And so this is like a sort of a theorist's conception of what the phase diagram for nuclear matter might be like. The idea is that we have density from low density to high density along here, and then we've got low temperature to high temperature here. And you can say, well, the early universe corresponds to sort of this kind of system like this, and the LHC probes really high temperature and fairly high density, and you got heavy ion collisions, like at RIC, for instance, that probe this area up here, very high temperature. But neutron stars are really down at a very low temperature regime at very high density. And this is something that is just really hard to probe with experiments with colliders. And so, although there are experiments on Earth, like I can't remember now the name of the facility, but there's a place in Michigan which is going to be probing a bit more towards this direction. Neutron stars in astrophysics are probably your best way to get information about very high density material. And so what we do is we try to relate observables, things like the mass and radius of a neutron star. We can relate those to properties of the equation of state of a neutron star, which is a relationship between the pressure and density of your material. Remember, I said that we're essentially at 0 temperature, so we're not worried about temperature. And you've got your equations of stellar structure that relate those. And the idea is that your equation of state is coming from your basic physics of understanding of what kind of composition you have, and trying to understand how to compute the properties, which is actually very difficult. And things like, are you getting some strange quarks or not? There are various processes that can take place that would soften your equation of state or make it stiffer. And we try to get an understanding of measurements of the mass and radius of a neutron star by somehow sampling the exterior space-time, which is highly curved because of general relativity. And we try to basically make measurements of these masses and radiuses of neutron stars in order to understand which of these equations of state might be correct, which might give us some insight into what's happening inside of neutron stars. And if you had that information, that would allow you to infer all sorts of other interesting things. For instance, you could then start understanding better things about the properties of superfluidity in neutron stars, or almost any other measurement. You could sort of get rid of that uncertainty of the uncertainty equation of state if we actually knew what it was. Now, this is the kind of thing that we are looking at usually. What happens is we have lots of different theorists have come up with different proposals for what the interior equation of state of a neutron star might be. And each one of those proposals, you basically solve the equivalent of hydrostatic equilibrium. We call it the TOV equations. And that gives you a range of possible masses and radii that stars can have. And so, for instance, the blue curves correspond to different equations of state and the possible values that you could have. And I'm looking at this and I'm saying, oh yeah, I think I forgot to extend this down to lower masses, just because we don't really think that masses below 1 solar mass really exist. Okay, for neutron stars. And so you have different equations of state. You've got this one over here. We're not going to worry too much about the details of what these things are, but you got this one that allows this range of masses and these radii, and no other masses and radii can exist. Now, there's also the red curves, where I just plotted the values that they would have if they were also rotating. And so, for instance, we have neutron stars that rotate at 600 hertz, and you can see kind of how that affects them. And what happens is you might expect the larger neutron stars, the ones that are 12 to 14 kilometers, they're bigger, which means the centrifugal force affects them more, and they get more deformed by rotation. And so you can have much, well, if you believed, no one believes this equation of state, but if you did, this would tell you that it would get highly deformed. Okay, so this is kind of the theoretical picture of different predictions of the properties of masses and radii of neutron stars. And the question is, presumably, only one of these is correct, okay? You could say maybe there's some sort of weird phase transition that might bring you from one curve to another. But I think for now, let's just think about it as we really only think that there should be one equation of state for nuclear matter. And we would like to basically do measurements to figure that out. And so the thing that people have kind of vaguely in their head is the idea is I just created some fake measurements of masses and radii of neutron stars. And lo and behold, they all more or less lined up on here. And the idea is that you'd like measure thousands of neutron stars, gets how big they are, what their masses are, and that will tell you what the equation of state is. And so this is like an idea that's been around a long time, and it's been shown by, say, Lee Lindblom that this is a well-posed problem to invert this and figure out the equation of state from it. But it's, of course, not as easy as all that. The question is, of course, is how do you get masses and radii? So masses, you know, in astrophysics, that's usually something that you can often get if you have a binary system. And so there are certainly masses. And the most interesting observations of mass most recently are the highest possible masses that you can measure, because each equation of state has a maximum mass that the material can support. And this is sort of like the Chandrasekhar mass for white dwarfs. The problem is that for neutron stars, we don't know which is the equation of state, and so we don't know which is the correct maximum mass. And if you knew what that is, that would also help you with identifying black holes, of course, too. And so the nice thing is that with this observation, there's 2 neutron stars that have masses very close to 2 times the mass of the sun. And if you look at this line here, you can see that there's some equations of state like this one over here that cannot make a neutron star with a mass that high. And that says that one is wrong, okay? And so we can use that to basically get rid of some of the neutron stars that are here, and allows us to keep some others. And we can say, okay, this one's sort of marginally allowed. And so that's kind of interesting. And so that's one of the big pushes in observations, is to get as high mass neutron star measurements as possible. I think the observation from Lisa might, LIGO might suggest maybe a slightly higher mass, but I think it's probably not as good error bars like to constrain things here. So I'll just comment on just one project that I was working on, was sort of going in the less interesting way. Is we found, okay, there's something, this isn't the main purpose of my talk here, but anyways, there's something called the quasi-periodic oscillation that you see in the X-rays of accreting neutron stars. And you'll see that there's an oscillation at a particular frequency. And in particular, there are some frequencies that are around, say, 1300 hertz, which is about what you would expect something that is orbiting near the innermost stable circular orbit of a neutron star. That's the orbital frequency, approximately what you would expect. And so these observers, Marijke van Dorsburg and Michael van der Klees, were observing these QPOs, and they were able to find this one particular system had this very high QPO, and they were wondering about how to interpret this if you were to say that suppose this frequency that they're seeing is actually due to orbital motion, which is not a given. That might not be a correct interpretation. But if you just say it's orbital motion, and it should be something that's orbiting the neutron star that is at no closer than the innermost stable circular orbit, you know, in general relativity, that you can't orbit anywhere around a neutron star. Anyways, you could at least try to find out what that would tell you. And so what's interesting is that the different equations of state, these are predictions. This is an observation of an orbital frequency. And if we just say that this is the frequency that you would have if you were at the ISCO, it turns out this is moderately independent of the equation of state. And as long as you just say that you're outside there, that tells you that you have to have a mass for this neutron star, which is about 2.1 solar masses or less. Any of these would be okay. So that doesn't really tell you that much about the equation of state, just because, well, it just tells you that you have to have a mass less than this, which doesn't rule anything out. But I thought it was kind of fun that we were able to do that. And if they were to measure higher frequency QPOs and interpret it the same way, it would actually start ruling out some stiff equations of state. But anyways, the main interest that I've had is the question of how do you actually measure radius, which is a much harder problem. Because you could have this silly idea in your head of what we teach in first year astronomy, that you just sort of measure the angle and figure out the size, but of course that doesn't work. These things have a radius that's about 10 kilometers. You can't possibly resolve it unless you got an amazing ISM lens or something like that, which is going to allow you to do that. Okay, so one method that people use is called the Blackbody radius method. And the idea is that this is like another sort of standard first-year astronomy problem. You sort of say, I've got this hot sphere, it's uniformly radiating, and I know the distance to it, and I can, from its spectrum, I can figure out the temperature. You can just use the Stefan-Boltzmann law to figure out the temperature. And what you do is, in general relativity, you say, well, okay, that radius that you're going to get is going to be called the luminosity radius, RL, and we have to correct, but it's well understood how to do that. Now, that's obviously an oversimplification, and because, in particular, neutron stars aren't going to be pure black bodies. They're going to have more complicated spectrum. But this idea has been applied to a number of neutron stars, mainly those that are in X-ray binaries. And what happens is the neutron star can go through periods when it's in outbursts, which means that it's getting a gigantic amount of material accreted onto it from the accretion disk and its companion, in which case you have X-ray bursts, which are small explosions that take place on the surface. And that could possibly be giving you emission from the whole surface, and people have done applications of that. And then also you have periods of time that are called quiescence, which are in between times of outbursts when there's very little accretion, in which case you just basically have the residual heat from the surface being radiated away. And so people have done observations in both kinds of systems where they just basically assume that they're looking at light coming from the whole star, and they can do observations either of the quiescence or the X-ray bursts. And I'll just comment that both of these types of observations have a lot of assumptions that go into it. For instance, what kind of spectrum you're using, and a lot of details about how to choose which data you're looking at. But they all can come up with some values. Most of them are not particularly constraining, and none of them agree with each other. So it's kind of still in a field that's kind of still fairly new. I'll give you an example of just one recent observation, which I thought was kind of interesting. And so this is a method called the cooling tail method. This is not my own work, so I'm just sort of presenting someone else's as something kind of interesting here. And they basically have an X-ray burst. There was photospheric radius expansion because it reached the Eddington limit, and then the material falls back on the neutron star and it radiates, and they've got a way to identify what they're looking at. And anyways, through various assumptions about the atmosphere, they're able to say that there's sort of this range of I think a reasonable level is kind of in here, of possible masses and radii. And at this level, it's, I would say, still probably a little early to say that this is something that has been definitively measured, but it's sort of a direction that people are going in. One thing that I'm always kind of interested in is what happens if the star is spinning, and how does that affect your observations? And in particular, in this measurement that they were doing when they were observing this system, you can see oscillations, and you can tell that it actually spins with a frequency of 330 hertz, which is relatively fast. And this is an analysis. Because it's a difficult analysis, they're just basically assuming that it's a spherical star. And so you might ask the question then, how does rotation go ahead and change your observation or your interpretations of observations? And just, I think a simple thing that you can think about here is, suppose a star is rotating and it's going to become a squashed oblate spheroid. And suppose that you compare a oblate star with a spherical star, and they have the same equatorial radius. Well, the oblate star has a smaller surface area. And so if the real object is an oblate shape like this, because it's rotating rapidly, but you analyze your data assuming that it's a sphere, in order to get the smaller surface area of the real thing, you're going to have to kind of artificially measure a smaller sphere radius in there. And so you're going to underestimate the sizes of the neutron stars that way. So that would be an overall systematic effect that you might expect. And so one of the things that I'm working on with one of my students is trying to improve how we deal with that. Some first work that was done that I did in collaboration with a group at Arizona was to do just sort of pure black body and not use realistic atmospheres. And what we found is that for very rapid rotation and pretty stiff equations of state, which might not be believable, you actually can get about a 3 to 5% underestimation of the size of the neutron star using this method, assuming that you knew everything else well enough, which you don't. And the idea here is this is the true radius of the star, and this is what we call the luminosity radius if you assume that it's spherical, and this is the luminosity radius if it's a deformed sphere, and this is taking Doppler shifts and everything in there. And what happens then is that if you knew that you had this particular mass and you measured luminosity radius of 14, you would think it's got this 11-kilometer radius, but the true value would be over here and it should be larger. So that would lead to some systematic errors.
How much does the spectrum differ in the black body?
Oh, it's sort of vaguely black body, but I believe it's more beamed is what happens. But I'm not actually too sure. I don't know that much about the spectrum.
Systematic effects. Well, I mean, the systematic effect to the spectral effect compared with what you just described.
My suspicion is, okay, so we need to actually do this calculation still, but if you have more beamed radiation, that is going to lessen the effects of the geometry here. And so I would think that like a hydrogen atmosphere, which is more beamed, this will not be as important an effect. But if you have sort of anti-beaming, where you're going to get a lot more light emitted closer to the tangent, that should be sampling the parts of the neutron star which are geometrically affected by rotation more. And so that's my guess, is that, so Compton scattering, for instance, would lead to more of a fan beaming kind of thing. That's my guess. But I'm hoping to have better answers to your questions, maybe in a year from now.
The factor you get for the difference between the radii which you measure and what you predict, could it be coming from something like a square root of 2? Because if you have a sphere, you have 4 pi r squared, and if it was just a plate, the actual surface would be something like 2 pi r squared. And if you just divide it out, then the radius you've measured would be something like the square root of 2 times what you...
It's quite likely that that's approximately...
Yeah. You have 1.5 and something like that.
It's probably mainly because when we're looking at the different ways that things come in, it seemed that most of the issues were not coming from things like Doppler beaming and stuff, which is also interesting, but a much smaller effect. I think most of it is coming from geometry.
I'm just compressing the sphere into a
Yeah.
and seeing...
Yeah. That's probably a good way to think about it, actually. Yeah, and especially because we have all sorts of interesting universality things happening in neutron stars that could definitely go in there. A totally different thing, which is maybe not necessarily related to rotation, is just the question of people assume these things are perfectly uniform, and so that the whole star is emitting. But you can imagine that maybe there's some hot spot. And so if what you have is a star that is mainly cool and it's got a hot spot, and you can't resolve that, and you just assume that you're seeing one temperature, what you're going to be doing, if you just think of just about pure black bodies, is that's going to skew the little bit of, when you add 2 black bodies, it skews the effective temperature a little bit to the blue side. And so that means that if you analyze this by assuming that you have a perfectly smooth temperature on your neutron star, that means that you're going to infer a hotter temperature, and you sort of compensate with a smaller radius star. And so assuming that your star is perfectly uniform in its emission could lead to also similar kind of errors. And my guess is that this might be more likely. It's hard to say because the kinds of systems that people look at, maybe you'd expect it to be smooth. I don't know. Other people might have a better feeling for that. Okay. So talking about hotspots, that leads me to sort of the most current kind of things that we're interested in. And this is actual hotspots that give you pulsed emission. And so the idea here is there are some neutron stars where there's definitely hot X-rays emitted from the surface of the neutron star. And we see it as pulsed emission. And there's a lot of interesting gravity effects that happen when you have this. And so what we have here is a very nice animation which comes about from an undergraduate student who's working with me probably more than 10 years ago. I thought, hey, this would be a fun project, is to actually come up with a way to make visualizations of this. And so he did that, and then more recently, as part of the NICER project, they were wanting some nice visualizations that were scientifically accurate. And so the NASA people went and sort of made it look a little bit nicer here. So what happens here is, this is Newtonian physics, no bending of light rays. And you have a hot spot, and you can see it for exactly half the period. And that gives you a plot of brightness versus time, where you have a long eclipse here. And then what happens is, when you have general relativity, you can see light from the backside of the star, and it bends around, and you can see it. And you can see the poles here, for instance. And as the hot spot moves around, it gets deformed into a bit of a ring as it goes around. And so basically, you can see the light for the whole time. Yes?
Does general relativity also make the size of the neutron star a little bit bigger?
Yeah, that's right. And so the apparent size is larger. And so it basically, if you're seeing light from the back of my head, and so you're seeing like my hair over here, I would look like I've got a bigger head, right? And so that's part of that whole thing with the luminosity radius. The luminosity radius that you measure, it looks like a larger radius than the true radius of the neutron star. Yeah, and so you get all these deformations here. The other thing that might not be quite as obvious, but I put a very high spin of a third of the speed of light at the equator here, so that you could get more easy to see special relativistic effects. And let's see if you can see some of this. So first of all, Doppler boosting means that the blue shifted part of the star is going to be brighter to your eyes than the red shifted part of the star. And so you can see now this part is red shifted and it's dimmer, and then the brighter side is the yellow side. So this is the blue shifted. And then we also have all the aberration effects in here as well. So there's deformations in there from special relativity as well. Okay, but the most important thing is you can see that because you can see the spot for the whole period, in this geometry that I've chosen here, we don't have eclipses, and we have less modulation in our light curve. And so increasing the strength of gravity decreases the modulation of a light curve. Okay, so there are actual systems where we think this is of interest. And you have accreting neutron stars, where material is being funneled onto the magnetic poles, or so we think, and then you get hot spots, and so those are the accretion-powered millisecond pulsars. And so we see X-ray emission of this pulsed form there. That's probably from that. There's also oscillations during X-ray bursts, which are probably also coming from hot spots on the surface. Both of those are very difficult to analyze. They tend to not be very steady. The nice and steady version is the rotation-powered pulsars, which are not accreting, but you have return currents, which presumably heat up the surface and give us the X-rays that we see. And so basically, you get X-ray emission from the magnetic poles of the pulsars. And so that's the X-ray emission, and of course, the radio emission is coming out from further out. And so the nice thing is that the X-rays, we think, are coming from the surface of the star, as opposed to studying radio waves, which would give you information about the magnetosphere and stuff far away from the star. And so if you want to know the properties of a star, you really got to get some light from the surface. So the NICER X-ray telescope is targeting rotation-powered pulsars to allow us to see pulsed X-rays from the surfaces of these neutron stars in order to try to basically look for these kind of signals and to understand the properties of the neutron star. So I'll just comment. I don't know how many people here have dealt much with X-ray timing, but of course the most important X-ray timing mission was the Rossi X-ray Timing Explorer, which has since died, but there's lots of nice legacy data. XMM can do some timing, but it's really an energy spectrum machine. AstroSat, which has Canadian content, does X-ray timing, although it hasn't done very much with neutron stars yet. And then, of course, NICER, which is sitting on the International Space Station, was basically designed to do this type of observation. And so it's got the right energy response and timing abilities to do that. And then there's this one. NICER could possibly, it's going through a NASA panel review right now, so it might actually be able to keep going for another 3 or 4 years or something like that. So hopefully that'll happen. In the future, there's a Canadian collaboration trying to propose something called Colibri, which would be kind of like NICER times about 3 with better X-ray energy resolution. I'm not sure how likely that is to get funded, probably 0 probability, just knowing the CSA, but who knows. And then there's 2 big proposals for timers. There's the EXTP and StrobeX, which would be totally amazing. And they're going to be sort of like the old Rossi X-ray Timing Explorer, but about 10 times larger effective area. And so EXTP is a collaboration between Europe and China, and StrobeX is an American one. And these things would also bring in polarization, which would be pretty amazing. Okay, so NICER stands for the Neutron Star Interior Composition Explorer, because we're basically trying to understand the interior of a neutron star by looking at these X-ray pulsations. And so this is sitting on the International Space Station, and well, there's some specs. I don't understand all the specs, and then there's some very nice pictures. Okay, so we have various working groups amongst NICER, and so there's a lot of different physics in astronomy which is being explored by NICER. Things like magnetars there's groups that basically look at the magnetars, and there's others that are looking at different accretion physics, for instance. But this group is basically looking at trying to get information out of the pulses. And the idea is there's 4 main neutron stars, and we would like to be able to infer the radius to within about 5% and the masses to within 10% in order to get some reasonable constraints on the equation of state. So the way this happens is basically you say, well, we just already mentioned that the stronger the gravitational field, which is the ratio of the mass divided by the radius, the less modulation you have. So that gives you one clue when you see different pulse profiles of plots of brightness versus pulse phase. So the high pulsations would be telling you low surface gravity, and low pulsations would be telling you stronger gravity. So that's one important information. You, of course, have to disentangle that with the fact that you don't know where on the star the spot is, whether it's closer to the spin equator or spin pole or the spin equator. That makes a difference. You also typically don't know where the observer is, what the inclination angle of the system is. And so those are big uncertainties, which causes trouble. The one important thing is that these kind of geometry effects don't depend on the energy. And then other properties are going to depend on energy, and that helps with the disentangling what's happening. And then the other thing that happens is that the speed of the rotation affects the symmetry of the pulse profile. And what happens is that if you imagine that my hand is emitting light, you normally would think that when my hand is sort of perpendicular to you like this, you don't see anything. And then as you see more of it, and it comes around, you can see more light, and it basically looks brighter when my hand is facing you, and then it gets dimmer and dimmer. So that's the way you normally think of it as being, except that you also have Doppler beaming in here. And what happens is that the intensity of the light is proportional to the cube of the frequency of the light. And so as my hand is moving towards you, it's blue shifted, and the intensity of the light is brighter on the blue shifted side of the star than it is on the red shifted star. And that gives you basically the peak emission. Instead of happening when it's directly facing you, the spot is a little bit earlier is its peak brightness. And so that gives you, when you have very rapid rotation, it gives you, when it goes from eclipse, it has a very quick rise to its peak intensity, and then has a slow fall off in phase. And so that gives you an asymmetry in the time, in that there's less time to get to peak than it is to get to from peak down to falling off. And so that is a signature that depends on the speed, but speed depends on the radius of the star, along with some annoying geometry here. And you always know the angular velocity. So that gives you sort of 2 key effects that are coming in here. Of course, there's a lot of other things, like you have to worry about the actual spectrum of the emitted material, about basically is it highly beamed, isotropic, or fan beamed. For the rotation-powered pulsars, because these things are not accreting, they've already had a lot of gravitational settling, which is very fast, taking place, which means basically that your lightest element is going to be at the top of the atmosphere, which is not very thick to begin with. And so you expect that your atmospheres are going to be dominated by hydrogen. And so the hydrogen atmospheres are fairly well understood. They're not exactly Blackbody, but they're vaguely Blackbody-ish. But what happens is that they tend to be somewhat beamed. And so what happens, this is the spectrum for light emitted normal to the surface, and then tangent to the surface is down here. But this is fairly well understood. So this is basically treated as a bit of a black box that goes in, but that's computed. And with that, you can make predictions about how the light is going to vary with time. There are some complications. You have to worry about, so I've always been very much worried about the oblate shape of the star, which sounds silly, but anyways, that's the kind of thing I worry about. You got other things you'd worry about, scattering. There can easily be multiple spots. You would expect two, right? Because, say, a magnetic dipole, but it's quite possible there's more. And these spots aren't necessarily circles. And some simulations would be suggesting much more complicated shapes. So the Amsterdam group, Tom Riley and Anna Watts, have come up with a nice method for making more complicated spots out of basically two spots that are circles with different temperatures and having them overlaid in different ways. And so these are kind of free parameters that end up going into the system. One of the things that I've always worried about was the shape of the star, and it turns out that does affect the pulse profiles in a strange kind of way. And so the idea here is that if the true shape is this oblate shape, but you model it with a sphere and you have light emitted over here, if you have an observer over here looking at the star, light needs to be emitted in this region number 1 in order to get to you, but if the star was a sphere, it would not be able to get to you. It would be eclipsed by the surface, and so you'd only be able to get light here. And so that actually has surprisingly significant effects on the waveforms that you would predict. So we have a way to deal with that in a simple way, which doesn't add extra parameters. There are 4 main targets for the NICER project. These 4 pulsars, who are, if you don't study pulsars, you don't recognize the names. But anyways, this is the closest millisecond pulsar to us. These all have spins in the, about 3 to 6 milliseconds or so. Some of them have known distances to us. In one case, we know the mass fairly well and the inclination. Some of them are isolated. We don't have masses, but we actually, these are going to be the targets of, they are the targets of NICER. Plus, there's one sort of exciting one which has a very high mass, but it's very low flux, so it's hard for us to observe. Yes?
What do you mean by inclination?
Oh, the angle between the spin axis of the star and the observer, and generally it's assumed that the spin axis is parallel to the orbital angular momentum axis because it's been accreted. So that's not necessarily true, but that kind of is our beginning assumption. And so this is the data that NICER has been producing so far. So it's basically, this is one pulse phase, and then this is the plot versus energy. And so you can see the pulses that are seen depend highly on energy. They tend to be in the soft part of the X-ray spectrum. There's about 2 megaseconds of data for this one, and 1 megasecond of data for this one. And so these two are at a state where there's analysis of these going on right now. And my guess is that should have results in probably by the end of the summer, maybe before that. These two need a little bit more exposure to be able to see the pulses properly. Now, this is one way to visualize the data in terms of sort of colors. A different kind of visualization, here we are, is one of my students sort of made this spectrum that oscillates in time as the star rotates. And so that's basically what we're trying to do, is we're trying to come up with a set of parameters that describes the rotating neutron star that we can fit the spectrum at every phase of the neutron star as it rotates. And so this is the basic kind of picture. So this is just a synthetic guess that gives something that's something like some old data. So the actual data analysis is kind of complicated at the moment. This is going with up to 4 different spots that have independent temperatures, locations, they're not antipodal, sizes, like whether they're tiny spots or large spots on the star, those are independent variables. Keeping a fixed hydrogen atmosphere, although it is possible in the cases where it's potentially possible that it could have a helium atmosphere because it's in a hydrogen poor environment, then it's possible to switch in a helium atmosphere. And then of course we don't know the mass, radius, observer's inclination. In some cases we know the distance reasonably well, so there's some various ranges of priors for these things. You got ISM extinction, you got some background. So you got all sorts of horrible things like the instrument response function and contamination by the aurora borealis and the sun. So there's messy stuff there. I don't know as much about that aspect of things. And then there's a Bayesian parameter estimation, which is basically being run at Amsterdam and University of Maryland. And the program that we've ended up finding that's worked out the best is called multi-nest, which is for parameter estimation when you have tons of parameters like we do. No. We are assuming that these are low enough magnetic fields that the magnetic fields are not going to be affecting them. And that would be kind of, my guess is that once the first analysis of this kind of thing is done, then it could be fun for people to then start saying, okay, how does things change when I add, say, strong magnetic fields, right? And so you could have the question of, does that affect like the propagation of light rays, for instance, or atmosphere? Yeah. Yeah. That's right. So this is low magnetic field atmospheres. So that'd be fun. But that's probably later on. Same thing that we are, for instance, assuming that general relativity is the correct theory of gravity here. And there are people right now who are looking at various scalar field gravities and stuff like that to look and see how much of a difference would you get if you then put in different theories of gravity, for instance. And that, again, is not something that we can do right now. That's just... I'm sorry, I can't hear you. Oh. Just basically, there's, I think, lots of heavy elements in the ISM that absorb X-rays. I'm not an ISM person. Maybe we have... Yes, we are, exactly. So we're dealing with the softest X-rays, not the hardest X-rays. And the softest X-rays are more highly absorbed by the ISM. And so that's a bit of a problem for us, because if my understanding is that the ISM doesn't cause as much extinction around 2 keV and stuff, but these things are mainly bright at less than a keV at, say, 0.3 to 0.5 keV, and that's where the ISM likes to absorb things. I don't know what the processes are for that absorption.
Oxygen K shell, carbon K shell.
So the time independent.
Yes.
Oh, yeah, that's right. This is just like in the region between them. Like, we're not worried about ISM extinction like right at the neutron star, which I don't know, maybe that's something people might worry about one day. Okay, so I'll just summarize by saying that I'm sorry I'm not providing you with any new exciting results, except that I'd say that it's looking like there ought to be results showing approximately 5% precision in the measurements of masses and radii of neutron stars, 4 of them. This would also be giving us information about things that you might be less interested in, like, for instance, the size of the hot spots. But for instance, I'll just comment that it's been seeming like we can't just use 2 spots, that 3 spots seem to be necessary. And these things aren't really antipodal kind of in any reasonable way at all. So that's kind of might be telling us something about magnetic field geometry, but that also might be something to do with our models. And so I'm going to stop here. Thank you so much for letting me talk.
I think we have several minutes for taking questions. Any questions?
Chris.
So, do you expect the emission to be polarized? And if we're to get polarization sensitivity, would you learn something new about that?
People have not been including polarization into these hydrogen atmospheres. I think that they are relatively thermalized, enough scattering that that's not an issue. But in a different system, the accreting systems, you have this electron corona on top of the hot spots, which then rescatters the X-rays, which are approximately Blackbody. And in the case of the accreting systems, you would expect your final X-rays to be quite polarized, I think. And in that case, something like EXTP could be really important for understanding the accreting systems. But I might be out to lunch. Maybe these things could be polarized as well. Maybe Chris has an idea.
These 4 different sorts of measurement, what is the distance uncertainty contribution to your mass radius?
I see. If there's a fair bit of uncertainty in the distance, that of course affects the radius a fair bit because they're kind of.
You say 5% given that you know the distance, or is that?
No, this is okay. So we're expecting better results for. Let me just show you the numbers that we have here. Here. This one, J0437, the closest to us, is known to exquisite precision. Okay, and that one's it's like a parallax measurement. This one, now that I'm looking at this, I think actually there's better measurements than what I have here. But you're talking about something that's not as bad as 10%, but it's maybe 5% error, something like that. So this is folded in, as opposed to these ones, which are going to have probably worse precision, and that's going to come in there. So these 2 are the first that we should have results for, and these are the 2 for sure that I think we should have good results for, partially because the distance is really not an issue for that one, and not enough of an issue for this one to be a problem.
I mean, 437 is really the queen of the sample. How many spots are you modeling?
So at the moment, most of the effort has been going into J0030, and so 3 spots has been most important for this one. But this one has very obvious interpulse. Let me just show you that to you. This one over here, I think quite like, so this is one period. And so it's obviously got a second spot, but it requires a third spot with potential different temperatures to give that information. This one over here, I'm not sure actually if it's going to need 3 spots or not, but it may very well actually. And so that's a bit unfortunate that it starts becoming a little bit rococo.
Well, multiple spots aren't conceptually difficult. I mean, they feel it's beginning to mess things up, but it doesn't. And then that's sort of starting to get a bit puzzling, isn't it?
Yeah.
So, running most of these neutron, you also have wind that produces a bullshocker, also wind nebula, and you also have high energy emission from that. So, aren't you concerned that this might contaminate perfectly?
So, I believe one of these has a no. Let me just think about it for a second. I believe it's this one over here has some kind of nebula around it. This one? Oh, yeah. So that's part of the. the background, but that's not the pulsed emission. But what's worse about this one is that there's a bright AGN really close to it. And so the reason why this is not the first one that we're looking at is that it has a lot of sort of bad background to deal with.
Does zero pulse phase, is that reference to the radio?
No. This is, I believe, just based on where it's brightest in X-ray.
That's not true for
Oh, you're right. Yeah, I don't know what was chosen for the reference there. It's possible that since these were both seen in radio, that maybe they combined it with the. I don't know. Yeah, I don't.
Yeah, the reference time that's being period, so it's shifting. The phase can be
So
shifting.
maybe two are really well aligned with one, and two are not. So I would guess that they try to align it with the radio or something like that. But anyway.
Yeah, that's an interesting point. Yeah. Okay.
Any more question?
This has been researched for 75%, so that surely must depend, you probably know that it depends on where, if you have 4 spots, where you put the 4 spots, right? You probably have done the reverse, where you make
Yeah, that's right.
that
Yeah.
and fit it, so.
Yeah, there's certain. Yeah, that's right. There are some values of parameters. So first of all, here you have pretty strong pulsations, and the fact that you see this is probably telling you that you're not just being lucky. Like we're able to see it well, and so it's going to be easy to pull things out.
So that's sort of, you sort of know that that's in a regime
Yeah.
where you're hoping to.
That's right. That's right.
Nice.
These two harder to say, really. But yeah, no, it depends actually what the different geometries of the angles are, whether it's easy to detect or not. And so when you're doing your synthetic data to see how well you can do things, it does depend on that, and that's unfortunate. So that's a little bit vague when you say plus or minus 5%.
But this is for a case that sort of looked like this.
Yeah, that's right. Yeah, basically we did a lot of synthetic data sort of tests based on things that were similar to what was seen in XMM's observations of this one.
Cable, the so-called queen had a mass.
Yes. In this case, use the mass. And so basically mass and distance where there's priors on there. So you have Gaussian priors based on sort of what's considered there. He also has a known inclination. So that's all coming from radio data. So in this case, you have a lot of extra information that you definitely want to make use of. In this case, there's no mass to be got, and so this one will actually provide an independent mass. Now, it's possible to go back and try to do this kind of thing where you say, okay, suppose that I don't assume this mass, what do I get? But the problem's hard enough as it is my feeling.
It's just some thoughts, like if the hotspot are polarized, so basically we can would it be possible to measure the number of hotspots with the polarization measurement with EXCV or stroke-X? And
Oh, interesting.
so those and then have the number of polarization.
Cool. I've got no idea. That's probably something to be looked at. Yeah, for sure.
If there's no more questions,